Hey, hey! Now you're going to learn what the reaction quotient QC is all about. Let's go! You probably already know the equilibrium constant Kc. With Kc, we can make statements about what the relationship between products and reactions look like when a chemical equilibrium has been established. But now, we also want to know how the relationship changes when the chemical equilibrium has not been reached. We want to know how the concentration of products or reactants will have changed by a certain point in time. We're talking about a net change. What's that now? So we'll take another look at the reaction equilibrium for the formation of hydrogen iodide. Here we also have a forward reaction and a reverse reaction. If more hydrogen iodide is produced, the forward reaction to hydrogen and iodine to make hydrogen iodide must be stronger than the reverse reaction, so more hydrogen iodide will be made than is consumed. Let's say we make 3 tablespoons of hydrogen iodide in 1 minute. In the same time, 1 tablespoon is used by the backward reaction. Overall, you get 2 tablespoons, 3 minus 1 so to speak. So that's a net increase of hydrogen iodide. You could also say that the net reaction direction is to the right or to the product side. It basically tells us whether the concentration of the products increases or decreases overall. This happens until the chemical equilibrium is reached. We can express whether we have a net increase of the product's concentration up to a certain point in time with another value. That's the reaction quotient QC. Somebody wanted to wind students up and decided to write Q in this curly style. Thanks for that, you baboon. But there are also some good things about QC. QC can be calculated by the same way as Kc, using the law of mass action. You only have to remember one formula. The difference between Kc and QC is that the reaction equilibrium has already been reached for Kc. That doesn't have to be the case for QC. The concentrations of the reactants and products are still changing. So, okay, how on earth does the Q value look now? If you look at the formula, you'll see the concentration of the reactants is in the denominator of the fraction. So if you have high concentrations of the starting materials, then QC is pretty small. Let's take a look at the bigger picture. With high concentrations of the reactants, you have a small QC value. On the other hand, if you have a lot of the products, the Q value is quite big. And here's the trick: to figure out the net reaction direction, you compare the QC value with the Kc value. With the Kc value, we already have a chemical equilibrium. And now, very important, remember, the QC value always wants to reach the same value as Kc. If the reaction quotient and the equilibrium constant are equal, then chemical equilibrium has been reached. That's pretty much the optimum state for QC. If QC is smaller than Kc, then we could say we have too much of the reactants. The net reaction direction is from left to right, so the concentration of the products increases. On the other hand, if QC is larger than Kc, the reaction direction is from right to left. It makes more of the reactants and the concentration of the products becomes lower. This overview is very important. Just hit pause and see if you have understood. Okay, it's important that you don't confuse the net reaction direction with the forward and reverse reactions. Think of our example with the tablespoons and hydrogen iodide. If QC is smaller than Kc, then the forward reaction and the reverse reaction both take place. But the forward reaction goes faster, so that the change in concentration from the reverse reaction is cancelled out. The net reaction direction is also from left to right. Okay, time for another example. Let's take our reaction of iodine and hydrogen to make hydrogen iodide. We'll assume that the reaction constant is 20.4 at 500 Kelvin. And these are the amounts of substances at the point in time we are interested in. Now, we want to see at this time, with exactly these quantities of our substances, which direction the reaction is moving in. Okay, now let's take our formula to help us calculate Q. Hydrogen and iodine are the reactants, and our product is 2 hydrogen iodides. In the formula, that looks like this. Now for a little trick. If the sum of the numbers before the reactants in the reaction equation is as big as the number before the products, you don't need to calculate using the concentration in moles per liter. Instead, you can simply use the amount of substance in moles. On the left here, we have 1 plus 1, which makes 2, and on the right, we only have 2, so a total of 2. So we can do this calculation using the molar quantities. Let's put that into the equation now. So, in the numerator, 0.3 squared, and in the denominator, 0.2 times 0.6. If you put that into your calculator, you get a value of 0.75 for QC. QC doesn't have any units. Now, if we compare QC with KC value of 20.4, then we see the KC value is higher. And when K is bigger than QC, then the reaction goes to the right. So the concentration, or molar masses, of the products increases. At our chosen point in time, the molar mass of hydrogen iodide is increasing. The amount of hydrogen and iodine is decreasing. What's important is to understand the difference between the reaction quotient Kc and the equilibrium constant Qc. With QC, a chemical equilibrium has not been reached yet, but with Kc, it has been. Then, when you compare QC and Kc, you can predict whether it will make more reactants or more products. So you should probably come back and take another look at this diagram. It's also important to know how we can calculate QC. You'll find more material about this topic in our other videos, so dive in, give it a go, and see you soon.